Hello YouTube, today I'll be making a quick video on a problem called the weighted job assignment problem, or rather the weighted job ordering problem. So this problem is fairly simple. All it says is that we have several jobs, each with length L, and weighting W. Now we want to order the jobs in a pairwise disjoint fashion such that our cost function for RS with n jobs is equal to the summation from I equals 0 to n minus 1, or let's just say from I equals 1 to n, of the weighting of job I times completion of job I. So for example, we have an array with 4, 2, 1, 3, 2, 2, where the tuple represents the length and the weight. We could have an arrangement that is 4 length, then 1, and then 2, and inside of here, so this is length 4, length 1, length 2, weight 2. My subscripts are bad because it's going to be confusing later on. So we have those weights. So naturally we get 4 times 2 plus, now we have 4 plus 1 times 3 plus 4 plus 1 plus 2 times 2. We get these weightings from the fact that this is the summation from over here, and this is the summation from over here, because these are the completion times. And the ones over here in green are the weightings. So the idea is to minimize this cost. So we want to minimize. Find S to minimize cost S and I. So the problem is we need to decide somehow on some factors in order to figure out which ones are we going to prioritize. How can we do these? So maybe some preliminary ideas are sort by the length, maybe sort by the weighting. You'll realize that you need to somehow combine these two approaches. So one perhaps technique of actually figuring out how to solve this problem is actually determine what you do in certain cases. So to gather a bit of intuition, we can consider two cases. So we will consider two cases. Given all equal, so if two jobs same weighting, which should go first? And likewise, if two jobs have the same length, which job should go first? So we have our case 1 and we have case 2. So for case 1, now we're going to solve this case. We have the following case. So we have some job 1, which has weight. So they have the same weight, but they have different length. So we have some length. And job 2, weight with length prime. So what's going to happen is, how do we decide which one goes first? these two jobs. So we could have job of length L followed by a job of length L prime, or we could have a job of L prime followed by a job of length L. Okay, so how do we decide between these two jobs? Now the idea behind this is let's actually calculate the score. So for job, the cost of arrangement of job J1, J2 is actually the weight times L plus the weight of L plus L prime. Job J2, J1 is weight of L prime plus weight of L plus L prime. Now, without lots of generality, let's say that L is less than L prime. Doesn't actually matter which one to pick, let's just say that. Then we say that J1, J2 is going to be less than J2, J1 because these are the exact same here, but this one is less than that one. So, therefore, all things equal, pick the one with a shorter length first, which sort of makes sense because you're actually decreasing the weight factor of W because both will end at the same time, but you want to essentially, since the weight is the same, you want to do a lower length, so your cost will be lower for the first block that you're actually placing, if that sort of makes sense. Hopefully my diagram helps more with that. Now we have our second case here, so it's a little more annoying. We have J1 is equal to some weight times L. Now we have job 2 with some different weight, both with the same length. So our diagram looks something like this. So we have some length, some length, some length, some length. Here we have W, W prime, W prime, W. So this is for J1, J2. So this is J2, J1. So we have J1, J2 is equal to WL plus W prime L plus L, and J2, J1 is W prime L plus WL plus L. Well, okay, let's just simplify these two. So we have WL plus 2L W prime. This one is W prime L plus 2L W. Without loss of generality, let W be less than W prime. And here we have a little bit of a tricky case because we have that this one is less than this one, but this one is greater than this one, so it's not conclusive. But let's do it another way. So let D equal to W prime minus W. So we're going to convert all of our statements over. So let's just let this be 1, 2, this. So we have 1. We're going to convert all of our W's over to W prime. So we're going to have W prime plus D L plus 2L W prime. For equation 2, we have W prime L plus 2L W. Hold on. So we have W prime plus D. Is it W prime plus D? We have W prime hold on. So use the difference between hold on. W. Use the difference between W prime and W. So anytime we have a W, we can add D to it to make it the same. So these should actually be minus here. Oops. Minus D. W prime minus D. Okay. So we have here W prime L minus DL plus 2L W prime L plus 2L W prime minus 2L D. Okay. So these two are the exact same. So we can remove these two over here. And we have this one is the exact same as this one. So in reality, all we have is from number 1, minus 2 dl, oops, minus dl, and here we have minus 2 dl, and of course, minus dl is greater than minus 2 dl, therefore we should pick the first one, and the first one was J1, J2, and we said that weighting prime is greater than weighting, so since we have that, we say that we should pick J1, J2. We actually want to minimize the cost, so actually we're going to pick the other way around. Since we want to minimize, we pick J2, J1. So we're going to pick the one, so all things equal. Therefore, all things equal, pick the one with the higher weighting first. Okay, so now we have two things. So in conclusion, pick shorter lengths first, and we also have to pick larger weights first. This is our heuristic right now. So when we sort or whatever processing we do, we have these heuristics that we want to pick. So we have two candidates that we can choose from. So we have two possible ideas. So our ideas are, let's have some ideas. We could do length minus W as our score. So the larger the weight, this puts more precedence. Smaller the length, the more priority we have, which sort of works here. As you see here, as the value of length increases, the priority decreases. So we're doing all these by sorting each job and making another score with a formula. Or another alternative is to do L divided by W. So the higher W is, the lower the score, and the lower L is, the higher the score. So this is good. So both seem good in practice. Turns out only one of them is right, and just so coincidentally, the second one is actually the right answer. You can actually disprove the first one by running a couple examples, so I won't be going through that. Now we need to actually prove that the second one is valid. So the way we're going to prove this is we're going to be using contradiction, and actually assume for the sake of contradiction that there exists a wrong arrangement of jobs, and then we're going to apply this theory of length divided by the weighting to actually make it correct. So in order to do that, let's just say that we're going to do a proof. So proof, and let's do this. So assume for the sake of contradiction that there exists an arrangement of jobs such that for job I and job K, I is less than K, but length of I by weight of I is greater than length of J divided by weight of J, and that arrangement is optimal. So essentially what we have is we have some jobs, then we have a job of length L, then we have a job of length J. In the other case, we would have a length of job J, then a length of job I. Now ignore the lengths that I put here in the diagram, that's not what's important. But the difference is, let's pretend that we're swapping them. Swap. So the idea is we're going to want to show that if we swap these two, we're actually going to derive a better result. So how can we actually swap these two? Well, what actually happens when we swap? That's the question we should be asking. So what happens if we swap? Well, if we swap, what will happen is we're going to be getting an increase of putting this job over here. So we will be increasing weight. We'll be moving this job over here. So we will be increasing by weight of I times the length of J. Why? Because we're initially multiplying weight of I here, where it terminates over here, but instead we're going to be moving it one more to the right here, and the distance that we're moving it by is the length of J, if that makes sense. So to say that again, we're increasing this because we're moving the terminating position of this person over here, which is multiplied by weight of I, moving it to the right by the length of Lj. But at the same time, when we're multiplying weight of J, we're only multiplying it less by the length of I. So essentially our delta here is going to be weight of I plus length of J minus weight of J length of I. However, we notice one thing. From our inequality up here, we drag this down over here, we get length of I divided by weight of I is greater than length of j divided by weight of j. If we multiply this out, we get length of I times weight of j is greater than length of j, weight of I. So we have, actually we have weight of I, weight of I. If we look over here, it's very nicely aligned. We have these over here, this one over here, and this one over here, this one over here. Since we have these two aligned, we have that our delta is actually less than 0. Because we have that this value over here is greater than the other one. So when we're subtracting, we're actually subtracting a larger number, and we're going to be getting a negative. So since our delta is less than 0, then we can safely conclude that we have a contradiction because we found a more optimal solution. So yeah, now that we found this, we have a contradiction, and this assumes that we need to have this certain precondition valid for all points. So yeah, since we have this, we have proved it, and QED. This is it. So just to recap, we picked this heuristic where we assign for every single job, we have this value L divided by W, and after we assign it to all of those L divided by W, we just sort in increasing order of that, and we assign the jobs that way. So yeah, the time complexity of this algorithm will be O of n for the first iteration, so calculating score of length divided by W for each job, plus O of n log n using your favorite sorting algorithm. So like if you're using Java's dual pivot quicksort, or intro selection sort, which is C++ STL sort, or merge sort or whatever, it'll always be O n log n, and then we just assign it to our data structure of choice for the output or whatever. These don't matter because it will be dominated by the n log n term. And yeah, that's the final solution. Thank you very much for watching. If you have any questions, leave them down below, and see you guys later.